So just to introduce you to the talk, to the flow of the talk, I'm going to start with a simple why, the motivation to the study, and then move on to where I'm trying to answer my main question, so the setting, and then I'll move to stress indicators. We're going to zoom into an area, zoom in space and in time to a local region and look at specific earthquakes. And then we'll zoom out and look at the regional area, regional scale via modeling. And then I'll leave you with a summary of the conclusions. So what is the motivation of the majority of my study on the early stage rifting in East Africa? That is, what is the role of magma in strain accommodation? Specifically, do magma or magmatic fluids contribute to dilatation in earthquake sources? I'll get to that more in a bit. And how does the magmatic system contribute to crustal state of stress? So to address these questions, we turn to the East African Rift. I'm not sure if you can see my mouse. I forgot to check that. But here's the East African Rift. It goes from the main Ethiopian Rift up here in the north, down through the Eastern Rift and the Western Rift around the Tanzanian Craton over here. And then it actually continues south to the southeastern and the southwestern rift. And I'm focused on this area around here, also known as the North Tanzania Divergence Zone, where the Eastern Rift kind of splits into three different branches. So as I mentioned, we're here around that triple junction, the divergence, I should say, divergence zone. It's not a triple junction. So it's located, here's a blow up of that small green box right there. So we're situated right around the border. This line right here is the country border between Kenya in the north and Tanzania on the south, at the southern end of the Eastern Rift. And specifically, we're focusing on here some names: Magadi Basin, the Natron, and the Manyara Basin. So that's right there. And this area is the most seismically active sector of the Eastern Rift. And here we see the reddish to orange yellow circles are double difference earthquake locations in the area from a local seismic array in 2013 to 2014. So those seismic stations are the purple triangles on the map. And this temporary local array enabled us to study this area in detail. It's also important to note that the Eastern Rift is a magmatic rift, as opposed to the Western Rift, which is known as poorly magmatic. So there are a lot of volcanoes, especially up on the Kenya side of the Eastern Rift. And then coming down here towards Tanzania, there are also a few volcanoes, but there's only one very active volcano. And that would be Oldonyo Lengai, that is currently active. So just to help you a little, so it's a slightly different map because it's from another study. It was from a nature study earlier this year. But here's Oldonyo Lengai, that tiny dot right there, and Galai is this volcanic shield, a little larger right here. And that tiny dot, Oldonyo Lengai right there, is, you might know about it, is the only active natural carbonatitic volcano, so the coldest lava in the world. The same area is known to have a high flux of carbon dioxide, probably mantle, a lot of it mantle derived. So the Natron Magadi Basin here represent the region of highest estimated tectonic gassing of mantle carbon dioxide in the East Africa. And it has been a region of persistent carbon-rich magmatism for approximately the past 4 million years. So that includes Aldonia Lingai, which is the only currently active one, but there are other several carbonatidic volcanoes in the region. And this carbon must be sourced from laterally advected, what we think it should be sourced from a laterally advected cratonic lithosphere that finds fluid pathways to the surface that result in the elevated levels of diffuse soil degassing. I should mention that this is a Tanzanian craton right here, hence it is much thicker. And then this is the rift area, which is a lot thinner. And this juxtaposition allows, we think, for the CO2, the carbon, to find pathways, to be concentrated in this region and find pathways because it's an extension to the surface. Now, the same area was a host to a dike intrusion in 2007. So again, here's Aldonia Lingai right here, and here is Galay. And here the lines represent where dikes were mapped from satellite and modeling. And these diking intrusion was accompanied, here's a timeline, accompanied by earthquakes, a swarm of earthquakes, and later effusion of Lingai it was accompanied by a swarm of earthquakes and diffusion in Lingai, which later transitioned into ash eruptions. And so diking here and eruption here makes us think that there's probably some sort of stress interaction in this system. So the 2007, here's a cross-section through this area, just north of Lingai and south of Galay. And the 2007 diking was probably sourced from a sill complex above a magma chamber. So we think, where's my mouse? Oh, we think there are sills up here, shallow sills, sourced from a deeper, lower crustal magma chamber, as imaged from seismic tomography and also by looking at the distribution of earthquakes in the area. That was from the local seismic array in 2013 to 2014. And so we think that the diking is actually sourced from these sills. And here we see the earthquakes that were associated with the 2007 diking. It's not quite where we plot, so that's the gray star here. That's not quite where we're plotting the red line, which is where we think that where the diking occurred. But because of the lack of a local array in 2007, this is within error. Could be right here in this sill complex. So we've gone through the why and the where. So now let's get into stress indicators. These are actually stress direction indicators. We're not necessarily looking at the amount of or magnitude of stress, but more of the extension direction, since we're in an extension setting. But before we head into more of the stresses, I want to discuss a little bit about beach balls because we're going to see a lot of that later. So the seismic moment tensor is a mathematical representation of a seismic point source. So it represents deformation at the source of the earthquake. So the beach ball that you may have seen around, we see a lot on when we talk about earthquakes and focal mechanisms. The beach ball is a 2D projection of the deformation around this seismic point source. We usually talk about three components of the seismic moment tensor. The double couple, the isotropic, and the compensated linear vector dipole. The double couple component represents shear on a fault surface. So most of the focal mechanisms that you've probably seen are double couple. And that's represented by beach balls with two orthogonal planes. So it's much like this figure right here and this first beach ball on this table on the right. The second component is the isotropic component, which represents volumetric change. So this would be, for example, a pure explosion or a pure implosion, which would be the last beach balls on the table on the right, would be represented as a pure black circle or a white, completely white circle. And then CLVD is a little bit more complicated for some people to grasp, but compensated linear vector dipole just means that deformation along one axis. So if you have extension along this axis, it's compensated orthogonal to it by compression, such that there is no volume change. And these can be associated with opening and closing tensile cracks. So those are the ones that are going to look like eggs, or like that would be these two right here on the table, where you would have a larger circle with a smaller circle inside of a different color. And then you're just going to see combinations of these three different components would result in what may be a bit funky looking beach balls to the untrained eye. So these are a compilation of some of the stress indicators that I've looked at and that we published previously in the region. The beach balls are summed focal mechanisms, so a summation of many focal mechanisms in the region. The black ones represent the summation of teleseismic earthquakes, and the blue ones represent the summation of local earthquakes. So that's from the 2013-2014 local array. And we've grouped them into these three boxes shown here. And we can see immediately that this middle box, in this middle box, the teleseismic and the local earthquakes have very similar looking beach balls. And these beach balls reveal, if we're looking at the t-axis, or that's this white dot that's plotted at the edge of the beach ball, it reveals north-northwest, about north-northwest extension. While other seismicity studies in the north and in the south, as well as our local earthquakes and teleseismic earthquakes north and south of that middle box, suggest roughly east-southeast or east-west extension. The green arrows on the plot are GPS relative plate motions, which also mostly reveal east-west, about east-west extension. And so it seems we're here that we're observing in this middle blue box a local stress rotation of about 60 degrees, where local stress field dominates the regional stress field that's mostly east-west in this region. So first, let's zoom in and consider some of the earthquakes that occurred here in this middle box to look further into this phenomena. Okay, so again, here's Oldonyo Lingay and here's Galay, and we're looking at earthquakes happening kind of roughly around between Oldonyo Lingay and Galay. So I performed waveform modeling on the biggest earthquakes that's magnitude greater than 3.5, as recorded by the Crafty Array, the local array in 2013 to 2014, to study their source, the source mechanisms of those earthquakes, which are represented here on this first plot as the beach balls. And you can immediately see that they don't look like double couple earthquakes. These moment tensors have, again, those three components. That's why they don't look as clean as you might expect a DC earthquake to look like. And here's one way that we visualize those different source components. ISO here is the isotropic that's at the top in the south. The top and the bottom of this plot. That's a volumetric component, if you remember. And then on the left and on the right, along the x-axis, would be the compensated linear vector dipole. So that's no volume change, just compensated on the orthogonal direction. And then DC double couple would plot on the source type plot at the center. And you can see that event A, which is here, if we do, we plot several acceptable solutions, we'll find that they're consistently non-double couple. So we're confident in the non-double couple source of a lot of these earthquakes. So here, this set of earthquakes are confirmed or found. The solutions are found via bootstrapping to confirm the robustness of the solution. And most especially the two large earthquakes of interest, so that's event A and event B, which are very similar, and they also happened on the same day within a few hours of each other. But there were only a few earthquakes that were of large enough magnitude as recorded by this local array. So that was only 2013 to 2014, 2 years, actually a little less than 2 years that we had data available during in this region. And we wanted to know if maybe these earthquakes were somehow related to the 2007 earthquakes when the diking occurred. And so to answer this, we look at data from a nearby permanent station and use template matching. So we're zooming out a little. We were here earlier, this Oldonyo, Lingay, and Galay. Here's the local array, the triangles. And KMBO here is a permanent station that's been there since 92. Which is far away enough to, and there's not really, besides KMBO and NBI, there's not a lot of other permanent stations in the area. So earthquakes, to say the least, in our study area were poorly located in the past, the smaller ones especially. And so I took waveforms, earthquake waveforms at KMBO associated with earthquakes in the Africa catalog, and then compared the waveforms with the 2013 to 2014 earthquakes that were, of course, also detected at KMBO. And we bandpass filtered the earthquakes to the same frequencies used for the moment tensor inversion. And the goal was to see if any of these past earthquakes matched on the three component waveforms any of our well-studied earthquakes in 2013 to 2014. And we find that, yeah, it seemed that the 2013 earthquakes matched some of the 2007 earthquakes, and also discovered two other earthquakes that also matched prior to 2007, with 90% correlation on the vertical and 80% correlation on the horizontal. So here are the horizontals, and Z is the vertical. The regional earthquake locations we find as plotted here can be about 20 kilometers off. Again, poor seismic coverage prior to our local array, so we're not surprised. And we propose that these earthquakes here probably also occurred kind of more clustered around the sill complex and where the dike occurred in 2007. It's important to note that the earthquakes we find are similar but not identical, which can be expected in magmatic regions where strain is distributed over fractures above the intrusion as opposed to just slipping the same fault. So we then conclude that magma involved faulting. This is the term that we kind of used and introduced in the paper. Magma involved faulting persistently accommodates strain over intereruptive cycles. So even when there's no eruptions or diking intrusions occurring. And so that was one study that we did that focused on the earthquakes. Now we're going to step out a little, zoom out a little, and look at the regional, a bit more regional scale through modeling. So how does this rift magmatic system contribute to crustal state of stress? We know that there must be a transcrustal magmatic system. We're very familiar with this figure right here by Kathy Cashman, with a lower crustal magma chamber and shallower sills. Magma-related earthquakes occur on faults overlying this magmatic system. So up here, with fluids such as CO2 probably using faults as conduits to the surface. So probably helping and assisting with the soil CO2 degassing and flux that we also detected previously. So how does this magmatic system contribute to the crustal state of stress? And so I compiled data from tomography, refraction studies, gravity, to build and constrain the geometry and properties of the model, which is density and seismic velocities. And then I used PyLith, which is an open source numerical finite element modeling code to model the system. The outputs were in terms of stress, strain, principal stress directions. Remember, I was very, the stress indicators that we were looking at were mostly concerned on the stress direction. So the principal stress direction was a way to relate the model and the data. And so I will compare these model results with data sets such as the earthquakes, focal mechanisms, and the GPS models. So here we have just a picture, cross-section of the topography that roughly corresponds to this cross-section here, exaggerated clearly. And we can see here a little bit of the northern flank of Oldonyo-Lengai and the southern flank of Galai. And then here, I performed 2D and 3D models. The 2D modeling was roughly this cross-section here, and the 3D model was, well, about this plus the same size south of the cross-section. And the area of interest is this tiny area right in the middle where Oldonyo-Lengai and Galai appears. And below that, we also placed the lower crustal magma chamber that was imaged from the joint gravity seismic tomography inversion. So the goal was to determine the relative contributions of different rift components to the stress or strain field. Here are 2D models, and I constrained the geometry is constrained from data. So the first one here is the effective surface topography. So that's just DEM placed on the model. We did try to also model an intruded sill based on the location of our sill complex from the earthquake studies, but that had a very little effect in the area with the scale of everything and the scale of the sill. We modeled magma chamber, an inflated magma chamber. Again, the location and size of it based on tomographic inversion. And then we modeled the thin crust, the geometry and location of the moho is based on receiver functions. And then we tried to put them all together, all the components, all the 4 components together. And then here on the last image, we add extension to all the components. And here on the top left, we have 1D profiles down the center of the plot, roughly the center of the plot right there. For vertical, the first one, is vertical component, and then the second one is XX horizontal stresses. And we find that we find large variations of strain or stress at depth, where whatever is happening, the amount of stress or strain that is felt at the surface doesn't necessarily reflect what the amount of stresses happening at depth, which makes a lot of sense, but we need to remember these things when we consider that GPS models and GPS measurements mostly constrain what's happening at the surface and not what's at depth. And earthquakes, on the other hand, are probably more reflective of the stress state at depth, wherever the earthquake is occurring. So large stresses at depth can drive deformation that may be overlooked if we're only looking at surface constraints. And so to really capture plate tectonic processes and plate motion, we need to move towards 3D and seek to quantify and understand stress strain variations at depth. And so we see here the effect of surface topography is very limited to very shallow depths around where we find large variations in topography next to each other. The effect of the magma chamber, again, is also high right next to it, but immediately diminishes as you get farther away from it. But when you add them together, they kind of cancel out on some areas and highlight stresses in some areas. In this case, they highlight higher stresses in the region between Oldonyo-Lingay and Galay. And once you add extension, then that increases the stress too in some areas. I should mention, I forgot, sorry, that the black lines on this plot are sigma 1, are the direction of sigma 1, the principal stress direction. In this case, we're using the convention, the geology convention, where sigma 1 is the principal compressive stress, which we also, in this modeling study, we use as kind of a representation, the line that would that we use as a proxy for the preferred orientation of magma or fluids. Because if you consider that magma would intrude opening towards the direction of least compressive or most extension, most tensile, then sigma 1 would be the path. And so that's what we generally use to interpret these kinds of plots. And so in a way, you can also see that here in these areas between Oldonyo-Lingay and Galay, we find areas where sigma 1 is near horizontal which would suggest areas where fluid might accumulate and stay, and also areas with more vertical, near vertical sigma 1, which could be areas where magma might find a way to the surface, which is also, interestingly enough, where the diking occurred in 2007. So the goal, in addition to doing the 2D modeling, we also did the 3D modeling. And so these are map view from the 3D modeling. The first image shows a model that only considers topography and the stresses from that. The second image shows the effects from without topography, everything subsurface, so the moho and the inflated magma chamber. And then the third picture shows all three components plus extension. I should mention the second component actually includes the silk complex, but at this point, it was a very, very small effect that we neglect that component. And the white lines on this plot are sigma 3, the direction of sigma 3, which is your, in a way, your extension direction. And you can see how in the area between Oldonyo, Lengay, and Galay, the direction of sigma 3 changes a lot depending on what we're modeling. And especially we see that it's the second image that is closer to the northwest extension direction that we observe from the earthquakes. And so what we think is important, we think therefore that the subsurface stresses are very important and influence greatly the earthquakes occurring in the region. And once we add in extension, I should say extension is a bit tricky. It was a tricky component to add because we were working with static models. And the amount of extension, we usually deal with extension as something that's occurring over time. So it was a little tricky to add. And so modulating the amount of extension with the other 4 components would be able to recreate the local stress rotation that we observe in the data. And so we went through, just to quickly recap, we went through the why, and we want to find out the role of magmatic systems in the evolution and the strain accommodation of an early stage rift. We focused on the early stage rift, the southern part of the East African rift, along the Eastern rift, and then we looked at different stress indicators, focal mechanisms, GPS models, and then related it to the 2007 diking in the region. We looked at earthquakes in the 2013-2014 local array in detail, and then extrapolated our results back in time by looking at a permanent station and using template matching. And then from there, we then try to recreate and figure out the local stress rotation from a modeling point of view. And just to leave you with the conclusions on fault magma interactions, earthquakes occur, we think that earthquakes occur across a swath of faults and tensile cracks above sills that respond to regional extension, as well as inflation and deflation of the underlying magma chamber. And the local stress field, as observed from seismicity, focal mechanisms, GPS, is due to an interplay between topography, subsurface magmatic stresses, and regional extension, with a bit of a stress on the subsurface magmatic stresses that are a very important component to consider in this case. And with that, Thank you. And I'm ready to take any questions. Oh, how do I do this?
Thanks, Sarah.
I see someone with a raised hand, but I don't know.
Oh yeah, well, we can, Joyce, I guess you're first, and then Larry.
Cool. Thank you so much for the nice talk, Sarah. That was really cool. So my question is really, when you're talking about diking and the magma chamber, what do you mean? Is it like a 100% melting or partial melt of a certain amount with a certain amount of melt? And how does it differ in the observations you made, in relation to earthquakes that you were showing, and also the modeling that you were doing?
Very good question. Let's see. So let me start with the dike because that was a specific event. The diking that occurred in 2007 was, at that time, we didn't have a local seismic array. This was mostly studied through INSAR and modeling regarding, determining the time progression and the location of the dikes. The magma never reached the surface, although there were breaks at the surface. So this picture right here is actually the eroded fissure on top of the dikes where the dike occurred. This was a photo that I took. That will be nearly 11 years after the fact. So very eroded. It wasn't this wide when the fissures first appeared. Yeah, so there was no magma that reached the surface. And then the question about the magma chamber is it's most probably mush and not, we don't really have a lot of constraints on what the magma chamber would, the composition of the magma chamber and the state of the magma chamber. And in my case, in the modeling, I treated the inflated magma chamber. I introduced a little bit of density contrast, but that had a very little effect on it. The inflation was the most important aspect, and that came up on the model, in the models mostly. And that was just a pressure condition. So I wasn't, yeah, so it is probably mush, not liquid. I can't tell you how much of it could be eruptible. But at least for the modeling, it was mostly just a pressure condition. Was that
Great,
did that
thank
answer
you.
your question, or okay?
Yeah, I'll let Larry ask the question.
Thanks, Sarah. Now we're going to go to one of the chat questions, and if other questions come up while we're doing this, feel free to raise a hand or add more to the chat. And this is a question from Larry. Larry can jump in if I'm not getting the gist of this right, but on slide 7, the map at left by Bear, are the colored lines dikes? And he has a question about their orientation wrapping around the volcanic edifice. It seems opposite to what I've seen for dikes radiating from volcanic centers. What does this say about the stress field and or state of the magma pressure?
Okay, yes. So yes, the different colors correspond to dates. There are dates at the top left. I don't know how big your screen is, but those are dates. And so each line kind of shows where the dike, which dike was active at which time frame. And yes, it seems that they are radiating. It's the opposite radiation if you're considering direction, if you're considering Gelai as the source of the dikes. But in this case, Gelai has not been active recently. And again, the only active volcano in this picture, and even a step, if we zoom out from this image, if the only active volcano in this area is Lengai, which is right there in the south. So we think that there's a magmatic system the magmatic system in this region probably extends to south of Galai, in which case then the radiation pattern makes a lot more sense. Just it's not coming from Galai.
Okay, I was wondering, I actually have another question.
Please go ahead.
And I wonder if you could go back to the slide there. You had one slide that had stress profiles as a function of depth.
Is it this one?
Yeah, that one. So obviously, if you're modeling stress, the areas where stress is perturbed, if it's, say, an elastic model, the areas where stress is perturbed are likely to be areas where you have different elastic moduli in different geometric shapes. And if you're considering inelastic processes, they would also include different rheologies of materials. It was a bit surprising. I was wondering if you could go into a little bit more detail about those plots on the left, because obviously for example, you're plotting stress in the moho at depths that are much shallower than you would expect the moho to be. And it also looks like normally I would expect normal stresses to increase with depth, but obviously these aren't monotonically increasing. So you must be plotting deviatoric stress or something.
Yes, I did fail to mention that. So the stresses that I'm plotting here, the stress magnitudes that I'm plotting has the gravity component subtracted. So it is something like the deviatoric, but not in the strictest sense, in that I'm not just taking away the maximum, what is it called? The mean stress from any stress tensor that I'm getting. I'm calculating the mean stress that would correspond to a reference model with no perturbations. So something with just uniform thicknesses, no topography, no magma chamber. So I'm taking the mean stress. What would be the mean stress? Mostly attributed to gravity in this case, from a reference model and subtracting it from all the other models to be able to see more of the variation. Because otherwise, you're right, if I just plotted them with gravity involved, you're just going to see a gradient that increases with depth.
Mm-hmm.
Now for the moho, so the effect of the moho, as you can see here for this plot, even though we're only introducing the perturbation here at depth, that's about, I think the shallowest would be about 30 kilometers, and then the unperturbed pre-rifting thickness at the edges is about 40 kilometers. This introduces a stress field above and below it. There's mostly part of it is because you're introducing this higher density material at a shallower depth, and that kind of introduces pressure in the overlying crust, and yeah, that's come out as a larger horizontal stress than I anticipated when I calculated them. That's this orange plot that kind of goes out into the surface, mostly horizontal though. The vertical stresses are small. I should also point out that these are different scales. This is 10 to the 7th and this is 10 to the 6th. So it's actually a lot. This is about 10 megapascals, and this is about 20 megapascals. So about half of the image. So it does look bigger, I guess, because I zoomed in on it. But yeah.
And why is, I mean, I'm probably just misunderstanding something, but it looks like you have stress in the moho plotted all the way to the surface from 40 kilometers depth. And obviously the moho doesn't extend all the way to the surface. So I'm not sure.
Okay. So this is essentially a cross-section down this specific plot, which plots the effect of moho. So what kind of stress perturbations across the column of the entire plate am I introducing when I thin the moho thin the crust compared to having a crust with uniform thickness without the thin and without this kind of moho outline. And so that effect introduces stresses up and down the column. That's why, so these are cross-section, a profile down these plots, these 2D plots.
Michael, you have a question?
Sarah, thanks for the nice talk and the excellent work. While this slide is up, if we look at panel I, do these stresses help us understand why the dikes didn't reach the surface?
I wish. No. The quick answer to that is no, because I didn't look at. I was looking at a larger scale. I didn't do the smaller scale modeling to find out if there was some sort of stress or material barrier at very shallow depths that didn't that prevented the magma from reaching the surface. As you can see in these images, the most shallow bits, the most shallow stress points indicate vertical sigma 1, which might suggest that it could facilitate it will facilitate opening and reaching for magma to reach the surface, but that wasn't the case. So there's probably more, we know there's more heterogeneity at the surface that can't be accounted for in these simple models. So yeah, it'd be very interesting to figure out though.
Thanks, Sarah. I guess I have a somewhat related question. I know you're emphasizing the static situation here, but as a result of both of your investigations, I wonder if you could comment on how you think the presence of magma might influence kind of the extension history, the thinning history, I should say, of a region. Is it important enough? Obviously, people have used various parameterizations for thinning rates as a function of depth in different extensional settings. Do you think the magma plays a role in this?
Are you talking about more evolution, long-term evolution of
long-term.
Yeah. So in my case here, especially at this stage in this region, at this stage of drifting, it seems that magma is playing a very important role in accommodating strain and introducing stresses. And so I would think that not just at this stage, but maybe a couple million years prior to this point, if you're doing, modeling rift evolution, you'd need to take into consideration the magma component, because without it, it wouldn't be a good not good. It would be an honest representation of the important forces at play at this stage. And so I think it's very important to put in the moho, the crustal thinning, and then the magma chambers the largest magma chambers, lower crustal magma chambers that result, that is produced after that. Because that seems to, at least in this area, influence strongly where earthquakes and intrusions are occurring.
That's great. Thanks so much, Sarah. Any last questions from folks? Sarah, if you have a couple moments, we might just hold on a little bit while we finish up here, but there's always a few questions that people just want to talk one-on-one with you. But
Sure.
any other big questions for anybody? All right. Well, thanks again for joining us. Again, we'll be starting the session back up in January. I think January 12th, I think. But I'll send an email about that soon. And also just to remind you, we're going to have a kind of a dual set of seminars next year, and starting in January. Some of these will be modeling collaboratory style seminars. So overview with a goal to try to talk about some of the issues of modeling magmatic systems, and then others that are related to early career researchers and their new products. So thanks everybody, stay safe. Good luck to everybody that's virtually attending AGU in the next couple weeks. And I'll see many of you in the new year. Thanks, Sarah. That was awesome.
Yes. Thank you. And Michael, I just saw your message. Yes, I'm a postdoc at UBC.
Good. And are you a Killam postdoc?
No, nothing fancy.
Okay. Who are you working with? Bostock?
Yes.
That'll be excellent. And are you in Vancouver right now?
No.